I mean, that's it. They're wonderful. We should always use experiments, correct? So I guess this is the end of my talk, and we can all wrap up and go home. But one second. What happens in situations in which doing an experiment is not possible? Let's think about this. There are many situations in which randomization might not be ethical, might be very difficult, too expensive, or even impossible. What if we want to look at the causal effect of an event that has happened in the past, right? I put here a silly example. Consider an economist is trying to figure out if tattoos actually affect youth unemployment. So I don't think it's very likely that an economist would get a grant approved for getting a tattoo gun and then trying his artistic hand on random young people in their dorms or nightclubs, correct? So, well, we're left only with observational data to try to make our impact analysis and to try to check on our causal effect. But we have a problem when it comes to using observational data. And that is that when we have observational data, generally the outcome variable and the treatment assignment are not independent. In simple words, we're not going to be comparing apples and apples and oranges with oranges, right? Imagine this world. Imagine a world in which only people who are very wealthy send their kids to college and people who are very poor just don't. Let's forget about scholarships and anything in between. Now, if in that world, if I wanted to check on the effect of college attendance on wages, and I just did what we do in the randomized control case, which is just take the mean of wages of the people who went to college and subtract the mean wages of the people who did not, would we actually get the effect of college attendance? And we would say no, because the two groups are too different to begin with to actually just curate this specific treatment effect. We know that the differences might come from very many other factors, correct? So we have some issue with selection bias here. However, as I said, we might actually find ourselves in position in which we only have observational data to deal with. Thankfully, there's a large toolkit of quasi-experimental techniques that can help us approach this type of problems. And since these problems can come in many forms, the way in which these techniques are approached also come in many forms. So I'm going to deal with one particular problem. Let's imagine that there's a treatment or a policy that happens at a specifically one point in time. So let's think about this. Suppose that now New York just completely bans smoking. Okay, it bans smoking today, April 16th, okay? And we want to know, maybe let me pick a date in the past, sorry, I'll be more clear. Suppose New York bans smoking on January 2nd, this year, 2020. And we want to know the impact of that policy on the rates of lung cancer, okay? Now, how do we know if this policy is the one that is affecting lung cancer and not, for example, the fact that young people are less propense to smoke? You know, so we might want to say like, okay, so I'd like a comparison unit. I would like to know what would happen in New York if this policy had never occurred. So maybe we can take something that is similar to New York. We say like, maybe New Jersey. New Jersey is kind of similar. Maybe Connecticut. Delaware? San Francisco, and you'll say, okay, now you're talking rubbish because those are kind of similar, but New York has a different economy. It has a different way of transportation. It has different levels of smog. It has all these other factors that, even though these other cities are kind of similar, they're still also significantly different in many ways. Okay, so these are imperfect. We shouldn't take them as controls. But what about us putting them in a blender? What about us like taking the similarities that they have consistently and weigh them in such a way that we can generate a synthetic New York, a fake New York, an alternate university New York, alternate universe New York, sorry, alternate university, okay? So if we can't find a perfect control, maybe if we have enough of good enough ones, we can generate one. Okay, and before this gets too esoteric and too weird, I'm going to go through the details of the technique itself. And at this point, you have a bit of a Q&A. Sorry. There's going to be a Q&A at the end of the session in which we can discuss this at length, but I would like you, I will take this a little bit slow. So if there's anything that you would like to interrupt, and for now, it's okay. So let us talk notation, okay? About this method in which we take these imperfect controls and blend them into making them a good one. So first of all, let us define our treated and our control units. So let's say that we have a time series Y1, that is time index from 1 to capital T, and a treatment occurs at time T sub 0, okay? So that says, okay, we have an outcome, say in this case, rates of lung cancer, and we have a pre-treatment period, which happens from time 1 to time T0 minus 1. And from that point on, the policy has been applied. So here I have how that policy would look. So look at the superscripts. One is the true series, and the superscript 0 means the series without the effect, okay? So from time 1 to T0 minus 1, we don't have an effect. From time T0 to capital T, we have this delta T, which is the treatment effect, correct? So then we have like the series without the effect plus the effect is what we have in the post-treatment stage, okay? So synthetic control simply says, okay, since you have this series, now we can grab as K many other series that are, we say are kind of similar, okay? And then we put them in a linear combination and try to fit them to the treated one in the pre-treatment stage, right? So we say like, there is some linear combination, our blender, right? Of this control, of these imperfect controls in the pre-treatment stage that is going to perfectly predict the treated unit. And then what we're going to do with when we learn the weights of that blending is going to be to extrapolate them into the post-treatment stage such that they actually fake what is going to be our counterfactual, what New York would have been without this policy. And then we're just going to compare what actually happened with this new synthetic New York, with this alternate New York, okay? And let's actually look at how that looks. So in the pre-treatment stage, we're going to solve this optimization problem in which Y1 is the vector of the outcome variable series in the pretreatment stage. Y0 is the matrix in which each column is one of the imperfect controls series for the same outcome variable. And W is a vector of weights. These are the weights that we're giving to the blending, okay? And those weights have a couple restrictions. They need to be non-negative, and they need to sum to 1, okay? And then there's this V matrix, which is any positive definite matrix that can be used for scaling the outcomes. A lot of people just use an identity matrix, but it can be cross-validated for as well. So you can think of this as some hyperparameter, okay? So as I said, once we solve this and we get the values from this vector W, we go to the post-treatment stage and we say like, okay, the counterfactual or the predicted New York, as if the policy hadn't happened, is just the true series of the imperfect controls times this vector of predicted weights, and then the predicted treatment effect is just the difference between what actually happened and this counterfactual. Okay? Two big assumptions here, of course, in case you were wondering. One is all of the members in the control units or candidate control units need to have had no effect from the treatment, correct? If we have some bleed over effect, this no longer works. And the second one, which is a bit of a more technical assumption, is all of the series need to be trend stationary for this to work. I'll go into a little bit more detail in that until the end, but as you know, that just simply means that the distribution of the trends not changing over time. All right. So what better way to nail this if not with an example? So let us talk about the seminal example on the very famous paper that made this method popular. And we're going to talk about German reunification. So upon the fall of the Berlin Wall, we had the reunification of East and West Germany. However, West Germany was a country that had much higher GDP per capita than East Germany. So it might behoove us to think, well, if we're joining East Germany to West Germany, did that actually reduce the GDP per capita of West Germany post-reunification? What would have happened if they had never reunified? So in the seminal paper, Abadi and Gardezabal actually tried to evaluate this question and find a causal answer. One second, I have a question. This data can be found in the American Journal or Political Science Dataverse, and that's actually called that. But let's get back to this. So let me show you a group of series from the Organization of Economic Cooperation of Development countries from 1960 to 2005. All right, and these are all countries in which you see that we have more or less common trends and relatively similar levels of GDP per capita based on 2002 dollars, as we did on Germany pre-reunification. So in the sense of the design for synthetic control, we could consider all of these candidate controls. And we can say like, okay, we can generate a synthetic Germany to figure out the effect of reunification. So let's see what happened. So after solving the optimization problem with the treatment year put at 1990, we actually find that only a few countries give us non-zero weights. And just in case you were wondering, this is all cut at the 2 decimal level. That's why you're not seeing very, very tiny weights for other ones. But I just want to reframe that these are the important weights. So we have Austria, Japan, Netherlands, Switzerland, and the United States. And all of those actually made up the blending that is generating our synthetic Germany for this case. Now, you might have wondered, is it really necessary to do this? Why couldn't we have taken the average of all these countries and generated this, the synthetic control that way? Why did we have to go through the whole like, oh, it needs to be linear, but it also needs to be convex through the restriction of the weights? Well, if we had only taken the average of them, and you can see, this is the treatment year, right? And the solid line is the real West Germany, and the dashed line is the synthesized Germany. As you can see, in the pre-treatment stage, we actually don't match very well with the true data, correct? So hence, the extrapolation is actually not really telling us what we need to know, which is how would Germany look if reunification had never occurred. However, when we apply the synthetic control, we get something more like this. And here we find that in the pretreatment stage, we have a very good fit between West Germany and the synthetic West Germany. And that led us thinking that this dashed line is what Germany's GDP would have looked like had reunification never happened. A little bit easier to interpret, I think, or a little bit more definitive to interpret would be using this gaps plot, which is just measuring the distance between the synthetic control and the true data on the y-axis. And you know, there's just year underneath, with 1990 being our treatment year. So we see that after 1990, we actually find that the true data shows that the effect is negative. So we see like, okay, so the GDP per capita actually takes a hit from reunification. Now, I know that that what has gone on the mind of all of you when you were seeing this is like, okay, but how do I know that extrapolation is good? How do I know that this gap that I'm seeing in the post-treatment stage is not occurring just because, you know, forecast power is lost over time? And I think that, as all data scientists probably do, when dealing with time series, you're thinking of backtesting. In the case of this literature, Abadi and Gardesabal call this a type of placebo test. So let us look a little bit at one simple backtest. So in this backtest or placebo test, what we did is we redid the synthetic control fit, but this time we said, okay, the pre-treatment stage is now up to 1975, and the post-treatment stage only arrives to 1990, which is the year in which the actual treatment happened. Let's see if the model we fit actually forecast well into 1990. And as you can see, this is remarkably good. Correct? So on that way, we have an assurance that this forecast or this technique is convincing in its forecast. And again, this all depends on that trend stationarity assumption. of course, the independence from the treatment for the controls. And then the second way in which we can check this is convincing is the following. So I'm going to take this graph, and here on the x-axis, what I have is the post-treatment period root mean squared error over the pre-treatment period root mean squared error. So we have that if they are very close to 1, that means that in the post-treatment, the two lines actually fit very well together. Well, if this number is very high, that means that they were breaking away. And what would be really convincing for us is that if there is an effect, then our treatment synthetic control, the unit which our treatment unit actually has a very high number for these ones, and all the other ones are actually below. So we see that for West Germany, we actually have a very high number. And for the other countries, we have significantly lower numbers. You might say though, hey, Norway and Greece are kind of high, but if we take them as treatment units and then run synthetic control again, but let's not forget that neither of these were part of any of our significant weights when we look back at this slide. So here we have those two ways for placebo testing, and this is what generates for us a fairly convincing argument that this method is good and that we can trust our results. So if you want to think about this methodology in terms of applications beyond what I've given you, which is, just this simple West German example, and beyond, the realm of econ or social science, we can very much think about independent lines of distribution. Also geographical is a very easy way to think, in which an extraordinary event has occurred. Say you are some kind of logistics company and a specific town has had an earthquake, then the way you can check and how sales have been affected in the weeks and months coming is comparing that town to the sales numbers of other towns which were not affected by it. I think that's more or less where I want to end talking. No, wait. I'm gonna leave the slides for everyone. For quick implementation, there are two packages, one in R and another one in Stata that can do this, that have canned ways to implement this methodology. They're really, really good. Jens Heinz-Müller has been a co-author with Abadi and Diamond in many of the papers relating to this method. All right, thank you. And let me stop sharing and let's. Okay, so I have this first open question that says, like, if I understand correctly, isn't the assumption the other units are impacted overly simplistic? NYC smoking ban being affected, but SF smoking ban isn't? No. So here what I'm trying to say is this policy only occurs in New York, and in San Francisco it doesn't, or in New Jersey it doesn't, or in Delaware it doesn't, and there's no bleed over from New York having this policy that would change the rates of lung cancer in New York, or the rates of lung cancer in any of these places. They need to be independent. So perhaps you don't like the example, but that's the basic assumption. I have more stuff on chat. Okay. Okay, so do we have any more questions?
Yeah, everyone feel free to ask questions for Pablo. You should see a Q&A box within the Zoom platform. You can just type your question and it will come direct to Pablo. We'll just pause for a minute or two to let some more questions come in.
And so we have an open one. Yeah, we can go over the weights one more time. If it's okay for me to share my screen again, I'll do that. So here, if we look at this optimization problem, what we have is actually trying to reduce the mean squared error of the distance between the treated unit and the control units as a sum of weighted control units, where the weights have the implicit constraint that they need to all sum up to 1 and be non-negative. And from this solution of this optimization problem, we actually, of this constrained optimization problem, we actually get the distribution of the weights. So as you can see from this slide, we have those requirements all met. Are we clear? Why is this method better than comparing lung cancer rates in New York before and after treatment? Sure. So the reason why we want to do this method is because we want to, there might be very many things that are attached to the lung cancer rates in New York, correct? So it might have to do with contamination, or it might have to do with, I don't know, specific demographic trends on how people smoke. However, if we want to know or vaping, I don't know. But if we want to know the specific impact of the policy itself, that's what it needs to be clear, right? We're trying to look at the effect of the treatment itself. The only way to really do it, as it happens in the general treatment control setting, is to have two comparable populations, one in which the treatment happens and another one in which the treatment does not happen, such that the only difference that can occur has to come from the treatment. In this case, the way we do that is, since we don't have two comparable populations, we invent this other one that just hasn't been treated at all.
Any last questions for Pablo from the audience?
Either way, if we don't have any more questions, and if you found it interesting, I'm going to give Nico I think they already have my slides. So, and please feel free to send me any later questions. The slides have a couple of links that might be useful if you want to know more about this methodology. And it's become extremely popular. There was an entire Journal of the American Statistical Association entire issue devoted to this method. So I really suggest that if you're interested in causal inference, especially about topics in which experimentation isn't possible, you give it a run. It's pretty cool. It goes pretty deep, actually. This is just the very beginning. All right. We good?
Okay, great. Thanks so much to everyone for joining us, and thank you so much, Pablo, for sharing this content. If anyone has any questions, feel free to email us at nico@comet.ml. And then Pablo, I could get your email address and we could post it to the Meetup page as well.
Absolutely. Thank you, everyone.
Okay, thanks so much.